We have seen two simple rules as far as the root locus branches are concerned, namely the root locus branches start at the poles and end at the zeros unless there are asymptotes. If the number of poles is greater than the number of zeros, then there are asymptotes for the zeros as the gain k goes to infinity or increases without limit. Whereas if the number of poles is less than the number of zeros, then it is the other way around. The root locus branches, some of them start from infinity and then move towards the zeros. And we are now looking at the next rule for the location of the root locus, namely portions of the root locus which belong to the real axis, or the other way around, as I said, portions of the real axis which belong to the root locus. Now the rule is a little more complicated, but not too much more complicated, and the easiest way to remember it is as follows. Think of any point on the real axis. For example, on our pole 0 diagram, here we have a number of poles and number of zeros. Some of them are the poles and zeros of G, the others are poles and zeros of H. And as far as the root locus is concerned, it does not matter whether they are of G or H. We are looking at the polynomial which involves both G and H. Now if you consider a point on the real axis, there are various positions that it could have. For example, the point could be here, the point could be here, or here, or here, or here, or here. In other words, the point could be on the positive real axis to the right of all the poles and zeros, or it could be on the negative real axis to the left of all of the poles and zeros, or it could lie in between two poles or in between a pole and a zero. We are excluding the poles and zeros from our consideration at the moment because we already know that the root locus branches start at the poles and end at the zeros. The finite branches, that is those which are not asymptotic, do that. Now the rule is as follows. Any given number, real number, that is any point on the real axis, will belong to the root locus. And what does it mean to say that a point will belong to the root locus? It means that point or that real number will be a root of the characteristic equation. We have looked at the characteristic equation earlier. A number or a point geometrically is on the root locus if the number is a root of the characteristic equation or a root of the characteristic polynomial. Now the rule says that a particular point or any particular real number is on the root locus if the number of poles and zeros to its right on the real axis is an odd number. So I will write it here, number of poles and zeros to the right are odd in number. Let me repeat, a point on the real axis belongs to the root locus if the number of poles and zeros to the right of that point lying on the real axis is an odd number. For example, consider this position here, which is to the right of all the poles and zeros on the real axis. This point here, will it belong to the root locus or not? Well, look towards its right. Are there any poles and zeros towards its right? No. So the number of poles and zeros towards its right is 0, and as you know, 0 is regarded as an even number. Therefore it is not an odd number. Therefore this point does not belong to the root locus. What about a point between this 0 at 2 and this pole at -1? Let us say a location here. Now will it belong to the root locus? Once again, look at the portion of the real axis to its right. Are there any poles and zeros in that portion? The answer is yes. There is only one 0. So the total number of poles and zeros to the right of this location is 1. Now 1 is certainly an odd number, and therefore this point will belong to the root locus. And by a similar argument then, all the points of the real axis lying between -1, which happens to be a pole, and 2, which happens to be a 0, all the points lying on this portion of the real axis will belong to the root locus. What does that mean? Once again, it means that each point or the corresponding real number will be a root of the characteristic equation or of the characteristic polynomial for some value of the gain Ka, for some value of the gain Ka. Now, in this respect, there is something which I did not state explicitly, but it was understood that the gain Ka that I am talking about is a positive number. I will write this therefore explicitly. The gain Ka that I am talking about is a positive number. If you remember, the characteristic polynomial, and I will write it again, was Gd Hd, the denominator parts of G and H, those two polynomials, plus Ka, this gain, into Gn Hn, the numerator parts of G and H, that polynomial equal to 0. This is the characteristic equation, or the left hand side of it is the characteristic polynomial. It is understood now we are looking at Ka which are positive, because normally when one talks about a gain of an amplifier, one thinks of the gain as being a positive number rather than a negative number. If I want to talk about a negative gain, then I will put a minus sign in front of Ka rather than say that Ka is negative. So, let it be understood that the gain coefficient Ka in the characteristic polynomial is positive. If that is the case, then this is the rule. A point on the real axis is on the root locus if the number of poles and zeros to its right lying on the real axis is an odd number, and therefore all the points of the real axis lying between -1 and -2, all of them belong to the root locus for some value of K. Not the same value for all the points. This point will belong to the root locus for some particular value of K, let us say K equal to 10. Another point will belong to the root locus for a different value of K, but for some positive value of K, and therefore I will darken this portion to show that this is a portion of the root locus which is lying on the real axis. And now we know that the root locus must begin, one branch must begin at -1, another branch must also end at 2, it must begin at some pole, say -1, a branch will end at some 0, say 2. In this case, I am anticipating what we are going to find out later, that the root locus will simply have a branch which goes from -1 pole to the 0 at 2, as K increases from 0 up to an indefinitely large value. And so in this case, I am saying ahead of what we are going to do, that this part of the real axis is not only in the root locus, but it is a branch of the root locus. Let us move now to the next region of the real axis. Let us say we consider a point here. Is it on the root locus? Once again, I look at the portion of the real axis to its right, find out if there are any poles and zeros to its right. There are, how many of them total? Poles and zeros. There is one pole, there is one zero, so total number of 2 of poles and zeros. 2 is not an odd number, 2 is an even number. So this point will not belong to the root locus portion, or this point will not be a part of the root locus for any positive value of K. Next we move to this region lying between -3 and -2. Consider a location here. Repeating once again, how many poles and zeros to its right? 1, 2, 3. 3 is an odd number, therefore this part of the real axis will belong to the root locus, that is each and every point will be a root for some value of K. And once again, anticipating what we are going to do when we look at some more rules, this portion lying between -3 and -2 will not only be a part of the root locus, but it will be actually one of the branches of the root loci. Loci is the plural of locus, because there is more than one, so I am using the word loci or branches. So here is a branch of the root locus which will start at -3, that is when K is equal to 0 or very close to 0. The root will be here, there will be a root very close to -3. With K very large, there will be a root close to -2, and for values of K between 0 and a very large value, the roots will lie somewhere here. So this is another portion that belongs to the root locus. Next, this region between -3 and -4, what about it? Is this point on the root locus? Number of poles and zeros to its right, 1, 2, 3, 4. 4 is an even number, so it is not an odd number. So this portion will not belong, or each and every point between -4 and -3 will not belong to the root locus. Lastly then, we look at a location here to the left of the leftmost pole or zero, namely -4. Considering a point here, what is the number of poles and zeros lying to its right? 1, 2, 3, 4, 5. 5 is an odd number, so this will belong to the root locus. So also every point to the left of minus 4. Therefore, this entire region will belong to the root locus. And once again, anticipating what we are going to do later on, the third branch of the root locus will start at the pole minus 4. That is, it will be near this pole for k very small, and as k increases, the root will go on increasing, and ultimately it will become very large in absolute value, but a negative real number. Now therefore, applying only the first two rules and this third rule which we have formulated today, we can more or less come to a complete conclusion about the root locus. That is, what will be the locations of the roots for various values of k. Because it seems that the root locus will lie entirely on the real axis, but it will occupy only a part of the real axis, and the conclusion is that there will be one branch of the root locus which will move from minus 1 to 2. For k nearly 0, it will be, there will be a root near minus 1. For k very large, there will be a root near 2. Another branch of the root locus will move from minus 3 to minus 2. For k small, there will be a root near minus 3. For k very large, there will be a root near minus 2. A third branch of the root locus is this one. It will start at minus 4 and it will go to infinity as k increases, and so that is the asymptote. Here we have 3 poles, so the 3 branch, there will be 3 poles and 2 zeros. 3 is greater than 2, so there will be 3 branches of the root locus. All the 3 of them will start at the 3 poles, one at each pole. There are 2 zeros, so 2 of the branches will end at the 2 zeros, and the third branch will go asymptotically away from the origin to an infinite distance. And in this case, a rule which I am going to state later on says that there will be an asymptote in the direction of the negative real axis, and so this is going to be the third branch of the root locus. Now, from this, is there something that we can conclude as far as, let's say, the practical utility of this scheme is concerned? That is, if this is the pole 0 diagram for some system and Ka is a gain which we have to choose, then can something be said about the choice of Ka? Now, as you can see, for Ka small, the roots are all in the left half plane. There is a root very close to minus 1, another root close to minus 3, third root close to minus 4. All of them are in the left half plane. So if you recall, this means that the system response will have exponential terms which go to 0, and this is one kind of stability that one talks about. That is, the system response due to initial conditions will go to 0 as t tends to infinity. Or if the input is an input like a step input, the output will not increase in amplitude indefinitely, but it will reach some steady constant value. For a very large value of k, however, one of the roots is going to be near minus 2, that is in the left half plane. Another root is way out here towards the negative real axis on the left side, that is also well in the left half plane. But the third root is going to be close to 2. 2 is not in the left half plane, 2 is actually in the right half plane, and therefore we will have instability for a very large value of k. And as we can expect, then, if you think of increasing k slowly from 0, then there will be a value of k for which this branch of the root locus, which lies between minus 1 and plus 2, will give you a root which is exactly at the origin. That is not in the negative left half plane, it is on the imaginary axis, but it is purely real. But for a slightly larger value of k, there will be a root in the right half plane, and therefore there will be instability. So whatever system we are thinking of for which this is the characteristic equation, or the G and H are such that this is the pole 0 diagram, then there will be a value of k. We can call it a critical value of k. So sometimes call it k critical or kc, such that when Ka is equal to this critical value Kc, then there will be a root at the origin which is not quite instability, but it corresponds to a steady state component which is not 0. However, for k greater than this critical value, there will be no steady state. the response will simply have a increasing exponential part, and therefore it will go to infinity. Therefore such a system would not be acceptable. So whatever system it be for which this is the pole zero diagram, we can conclude that this system is what is called conditionally stable. The condition being that the gain k should be less than kc. The gain k should be less than this critical value of kc. Now it is possible to calculate this critical value of kc, although it is not really a root locus rule as such. However, Evans gave that also as one of the rules for the construction of the root locus, and that determination of the value of this kc comes from another method or algorithm which is named after an English mathematician who in the 1880s, almost 120 years ago, gave a tabular method which enables you to determine this kc, the value of the critical value of the gain. And this technique is known as the Routh array or Routh's array, or it looks somewhat like a table. It is also called the Routh table, and the algorithm or the procedure whereby you construct the Routh array is therefore known as the Routh algorithm. And if you say that it enables you to find out a condition under which there will be instability or not, then it gives rise to what is known as a criterion of stability. And so this is sometimes associated or called as the Routh criterion of stability or instability of a system. So just with the first two rules about root loci starting at the poles, ending at zeros, or starting from infinity or going towards infinity, and this additional rule for real axis portions of the root locus, we conclude that for the system for which there are three poles as shown, -1, -3, -4, and there are two zeros, one at +2, another at -2, there will be a critical value of the gain k, namely kc, such that for k greater than kc the system will be unstable, for k less than kc the system will be stable. Of course, we also see that if the value of the gain k is not kc but only a little smaller than kc, then the root of the characteristic equation will be very close to the j omega axis, or it will be a real root which is a very small and negative number. Because of that, the corresponding time constant will be a very large number. Of course, what is large depends on an application. In some application 1 second may be large, in some other application 10 seconds may be large, in another application 10 seconds may not be that large. But if it is very close to the real axis, there is a possibility that the response is not going to be as short lived as you want it to be, because the time constant is not as small as you may want to be, and therefore one would like to avoid getting very close towards the imaginary axis and certainly not get into the right half plane. Now in this third rule that I stated, any poles and zeros of G or H which are not on the real axis have no effect. I could have, for example, a pair of poles in the complex plane not on the real axis, or I could have had a pair of zeros in the complex plane, and they could be in the left half plane or right half plane, or they could be on the imaginary axis. Let them be wherever they are. Poles and zeros which are not on the real axis are not to be considered for the rule that I have stated for determining the real axis portion of the root locus. For determining the real axis portion of the root locus, poles and zeros which are not on the real axis are not to be looked at. They do not matter at all. They are not to be counted literally. We only count poles and zeros, count them together to the right of a point on the real axis to find out whether that point is on the root locus or not. If the total count number of poles and zeros to the right is odd, then that point belongs to the root locus. If it is 0 or even, then that point does not belong to the root locus. That is the third rule of the root locus that I have stated. Now we do not have really enough time to go into all the details, so you should look up your textbooks, but some of you at this point may feel like asking, well, how do you get such a rule? That is, how do you come to such a conclusion that this is so? Now, there was a particular way in which Evans got this rule, and that was as follows. Let us once again look at our characteristic equation, which is GD/HD plus Ka times Gn/Hn equal to 0. Now, we can rewrite this as Ka equal to minus GD/HD divided by Gn/Hn. Now, this GD/HD and Gn/Hn are all functions of S, they are all polynomial functions of S. So, let me write that explicitly. Therefore, Ka is equal to minus GD S HD S divided by Gn S Hn S, and by the convention or the assumption that I made, GD, HD, Gn, Hn, each of them look like S plus some, they consist of a product of factors, each one of them looks like say S plus alpha. Okay, that is what it is going to look like. Now, on the left hand side we have Ka, which is the gain, which is a positive real number. On the right hand side we have a function of S. So, for what complex numbers S will the point which corresponds to this complex number S belong to the root locus? It will belong to the root locus if this entire thing on the right hand side is such that it is equal to a positive real number. S may be complex, we are not saying that we are only going to look at real axis portion of the root locus, of course that is the rule that I mentioned, but in general a point in the complex plane which corresponds to a complex number S will belong to the root locus if this bracketed ratio of two polynomials is equal to a positive real number, or if I get rid of that minus sign, then GDS HDS divided by GNS HNS, this whole thing equal to minus Ka, and minus Ka is a negative real number. I am excluding Ka equal to 0. So, this is negative. So, what are the S's, complex numbers S, for which this whole thing is negative? Now, negative, not only negative but purely real and negative. So, from this one gets two conclusions or two conditions, one of which concern modulus or amplitude and the other concerns angle or argument. Remember that when we have a complex number say such as S or Z, we talk about modulus of S or modulus of Z. What is that? That is the positive square root of the real part squared added to the imaginary part squared. If Z is equal to X plus Iy, then mod Z is the positive square root of X squared plus Y squared. So, this is called the modulus of the complex number. Similarly, we talk about the angle or the argument of the complex number. What is the angle or argument of the complex number? Well, the most convenient way of thinking about it is to plot the complex number in the complex plane. If the complex number is here, let us say, then what is the argument? The argument is obtained by drawing the radius vector from the origin to the point and then measuring the counterclockwise angle starting with the real axis, positive real axis. So, this is the angle through which I will have to turn the radius vector to become equal to the radius vector pointing towards the complex number S. Then this angle is called the argument of the complex number. One can write an expression for it, except that there is an ambiguity which always arises when we talk about the inverse trigonometric functions. So, for example, I can write angle of Z equal to tan inverse y divided by x, or I can also write it as cos inverse x divided by absolute value or modulus of Z. I can also write it as sin inverse imaginary part y divided by absolute value of Z. The only thing is, when we think of the inverse trigonometric functions, there is an ambiguity. Tan inverse of a number does not specify the angle uniquely, not even within multiples of 180 degrees. I suppose you all remember your trigonometry well enough. For example, here is the angle, say theta such that the point S is in the first quadrant, and here is another point which is in the opposite direction, which is actually minus S, that is in the third quadrant. Now the angle or the arguments of the two complex numbers are not the same. In this case the argument is theta, in the other case I have to go counterclockwise. The angle is actually 180 degrees or pi radians plus theta radians. So these two complex numbers have different arguments, but tan inverse y by x is the same for both of them. For this number S, y by x, y is positive, x is positive. For the other number, y is negative, x is negative. So y by x is again positive and in fact equal in value. So tan inverse has an ambiguity. Tan theta is the same as tangent of pi plus theta equal to tan of 2 pi plus theta, and so on. Similarly, there are ambiguities concerning cos inverse and sin inverse. So we define it, the argument, as the counterclockwise angle measured from the positive real axis towards the radius vector. So that being done, then from the condition that we have the modulus, we have the complex number GDS HDS divided by GNS HNS equal to minus Ka, which is real and less than 0. From this we get the following two conclusions. If I take the modulus of this big complex number, then this modulus is equal to what? This modulus is simply equal to modulus of minus Ka, but modulus of minus Ka is simply Ka. Remember, Ka was positive. So this is called the modulus condition, and actually it is used, or it can be used, to calculate Ka for a given S, if that S is on the root locus. So if the point S is on the root locus, then we can use this to calculate the value of the gain Ka to which it corresponds, and there is a geometric interpretation of this which we will come to soon. On the other hand, I can take the argument of this fraction. What about the argument of that fraction? That is equal to the argument of the number minus Ka, but the number minus Ka is on the negative real axis, and so what is its argument? Its argument is pi radians, or if you think in terms of degrees, 180 degrees. And of course, as you know, all trigonometric ratios, inverse ratios, are ambiguous within multiples of 2 pi. That is theta, 2 pi plus theta, 4 pi plus theta, minus 2 pi plus theta. All of these angles have the same given trigonometric ratio. Tan theta equal to tan 2 pi plus theta equal to tan minus 2 pi plus theta, and so on. So one can always add multiples of 2 pi to this, or subtract multiples of 2 pi. So I can write it as pi plus minus 2k pi radians, or what turns out to be, it's an odd multiple of 180 degrees. This is because, as we see, when we calculate the argument of this ratio, the sum may come out to be greater than 2 pi in absolute value, or greater than 360 degrees in absolute value, and therefore we will have to think of it as an angle which lies between 0 and 360 degrees, or 0 and 2 pi radians, or alternately an angle that lies between minus 180 degrees and 180 degrees, and that is minus pi radians and plus pi radians. So this kind of interpretation we always have to do for angles associated with complex numbers. The second condition is known as the argument principle or argument condition. Now all this would not be useful if there was no simple geometrical interpretation of what is going on. Fortunately, there is a very simple geometrical interpretation. Now, as I told you, we don't have time to go into great details about what's happening, so we'll take our particular example and I'll illustrate this for that particular example, and you should look up your textbook and go into all the details. So here is the pole zero diagram once again. Here is the 0 at minus 2, and here are the various poles and zeros, one pole at minus 1, a 0 at minus 2, a pole at minus 3, another pole at minus 4. So there are 1, 2, 3 poles, there are 2 zeros, and there is of course the gain Ka, which is positive. And what was the fraction GDHD divided by GNHN? Then GD corresponds to the denominator of poles of G and H. Therefore I will have terms like S plus 4 into S plus 3 into S plus 1 divided by G and Hn. G and Hn is given by there are two zeros, s plus 2 into s minus 2. So this is the fraction that we are looking at, GDS HDS divided by GNS HNS. Alright. Now we are going to look at the argument of this, that is, for a given complex number s, this is a complex number, what is going to be its argument? Fortunately for us, this s plus 4 can be given a geometric interpretation. Namely, if I join this point s to the pole or the 0, in this case it is a pole to which this factor s plus 4 corresponds. S plus 4 corresponds to the root minus 4, which is a pole. So suppose I join this pole to this point s. Think of that as a vector in the plane pointing towards this point s. Then this vector has a length. This vector makes an angle with the positive real axis if I consider the angle described in the counterclockwise sense. Now you can easily see that for this complex number s, the angle of s plus 4 or the argument of s plus 4 is precisely the angle made by this vector with the positive real axis. So geometrically then, I just think of the vector, join the pole to this point s, think of that vector, look at the angle that it makes, and as I said, root-locus method is mainly for human beings, for small problems. I immediately see this angle. Of course, it is what it is, I don't know exactly, it is 30 degrees, 50 degrees, 40 degrees, but it is an angle in the first quadrant, so it is something like maybe 20 degrees or 30 degrees. This is something which we can see immediately, right? That is for the factor s plus 4 or for the argument of s plus 4. For s here, the argument of s plus 4 looks like an angle which perhaps is about 30 degrees. It is certainly an angle lying between 0 and 90 degrees. Look at the next factor, s plus 3. Once again, s is 2 plus j2, I can calculate s plus j3, then take the modulus and argument of that, but instead I can draw the vector from minus 3 to the same point s. Here is a different vector, it makes a different angle with the positive real axis, and that angle or argument will be precisely the argument of the factor s plus 3. What about the third one, s plus 1? I have one more vector, it makes yet another angle. That angle will be the argument of the third factor s plus 1. Now we make use of a simple fact from complex number arithmetic. If you have a product of two complex numbers, then what is the modulus of the product? What is the absolute value of the product? It is the product of the moduli. Plural of modulus is moduli. If I have two complex numbers z1, z2, then modulus of z1, z2, the product is the product of the moduli. Mod z1, z2 is mod z1 into mod z2. Modulus of the product is the product of the moduli. That is something which can be proved, and again you already ought to be knowing it. What about the argument of the product of two complex numbers? Well, the angle or the argument of the product of two complex numbers z1, z2 is the sum of the arguments, angle z1 plus angle z2. The angle or argument of z1 into z2, the product of z1, z2 is the sum of their arguments. The modulus of the product is the product of the moduli. The argument of the product is the sum of the arguments. Remember this. It is not correct that the modulus of z1 plus z2 is mod z1 plus mod z2. Far from correct. It is also not correct that the argument of z1 plus z2 is the sum of the arguments. It is not for the sum, it is for the product somehow that this result holds. Product of modulus and modulus of product. Argument of product and sum of arguments of the two factors. This is the property of complex numbers. This being the case, then if I look at now the three factors s plus 4, s plus 3 into s plus 1, then what will be the argument of this product? The argument of the product will be the sum of the arguments of each one of them. But what are each one of them? Each one of them are these angles. So the argument of this numerator thing will be the sum of these three angles. Now if I draw this diagram to scale, I actually put the point S, put the poles and zeros properly according to the scale, then by using a protractor I can actually measure these angles. You should try it out. Do it for this problem with S equal to 2 plus J2, the poles and zeros as shown. Actually on a graph paper, draw the pole zero diagram, put the location of the point S, draw these vectors, with the help of the protractor measure the three angles. However, we see that these three angles are all going to lie between 0 and 90 degrees. In fact, they are perhaps around 20 to 30 or 40 degrees. So there is something that one can say about their sum also. Each one of them is a positive angle, so their sum is going to be a positive number. Each one of them is less than 90 degrees. Certainly it looks like that. So their sum will be less than 270 degrees. This is a conclusion which we can draw right away by simply looking at the figure. So the argument of the numerator when S is this complex number will be a number that lies in terms of degrees between 0 and 270 degrees. It's probably somewhere around 90 degrees or 100 degrees or 80 degrees or whatever it will turn out to be by making actual measurements. Now, what about the factors in the denominator? In the denominator we have S plus 2, so I have to again draw a vector from minus 2 to S, and I will have its angle or argument. For the factor S minus 2, I have to draw the vector from the location is 2 to S. So this vector corresponds to the complex number S minus 2. The argument of this vector is the argument of the factor S minus 2. The modulus of the vector or the length of the vector is the modulus of S minus 2. Now I have a product in the numerator, I have a product in the denominator, but denominator is one thing and numerator is the other thing. So I have a product divided by a product. Now that rule about modulus and rule about argument extends to not just product but also to a ratio of two complex numbers. Mod of Z1 divided by Z2, if Z1 and Z2 are two complex numbers such that Z2 is not 0 of course, then the mod of Z1 by Z2 is equal to the ratio of the moduli, mod Z1 divided by mod Z2. And the angle or argument of Z1 divided by Z2, the complex number Z1 divided by complex number Z2, is argument of Z1 minus the argument of Z2. So it is the difference of the two arguments, argument of the numerator complex number minus the argument of the denominator complex number. So if we look at our figure once again, the three numerator factors give rise to three vectors and three angles. The two denominator factors give rise to two vectors and two angles. So what is the total argument of this whole ratio? It is the sum of the angles corresponding to the numerator, which is what angles corresponding to the vectors going from the poles to this point under consideration, minus, because we have in the denominator now, the sum of angles, the vectors which go from the zeros to S, and that's the total argument of this ratio. And this, the argument principle says, is pi radians or 180 degrees plus minus multiples of 360 degrees. And therefore the argument principle or the argument condition is stated as follows. Instead of saying the angle made by the vector going from a pole or a zero to a particular point in the complex plane S, the angle measured in the counterclockwise direction from the positive real axis, instead of saying all that, one simply calls that angle the angle subtended by the point S at a pole, or the angle subtended by the point S at a zero. And therefore the argument principle simply can be stated as the sum of all angles subtended by S, the complex number under consideration, at the poles, minus the sum of all the angles subtended by the same complex number at all the zeros. This difference of two sums should be equal to pi radians plus minus 2k pi plus minus any multiple of 2 pi radians. If a complex number S satisfies this condition, then the complex number S will be on the root locus for some value of k. And what value of k? That value of k is obtained from the modulus condition, as we saw earlier, and the modulus condition was simply that the modulus of this complex number is equal to Ka, and we can see from the property of the complex numbers that we have discussed that this modulus will be equal to what? It will be equal to, instead of sum product of lengths of vectors from poles, lengths of vectors from the poles or joining S to the poles divided by the product of lengths of vectors joining them to the zeros. This will be equal to Ka, the value of the gain K. This was Evans's idea of how to locate or how to find out whether a given complex number S belongs to the root locus or not. And as we can see, it's a very nice graphical method, and if you draw things to scale, one can easily determine these angles and measure these lengths, or one can of course calculate with the help of the calculator all these angles and lengths, and therefore for a given complex number S we can find out whether the angle condition is satisfied. If it is, then for that complex number we can use this formula to find out the value of the gain K. So the argument principle gives you a criterion or a test for finding out whether a complex number S, that is a point in the complex plane, is on the root locus or not. Once you have identified that it is or it is not, then you proceed further. If it is, then this rule, product of lengths of vectors from the poles divided by product of lengths of vectors from the zeros, gives you the gain K, value of the gain Ka, for which there will be a root at S. This is the basis really of the root locus method. Of course, as one goes on, one uses other principles, like I mentioned, Routh criterion or Routh algorithm is also used, so also some more ideas. In fact, after Evans gave the method, a number of people gave some additional rules or contributed to its development. But this is the fundamental principle behind the root locus approach. Now, as homework, I would like you to once again repeat this with the point 2 plus j2, that is S equal to 2 plus j2, by actually plotting, find out if the angle condition is satisfied. If it is, then find out the corresponding gain K. You can do that for one more point in the complex plane, or choose any point on the real axis or on the imaginary axis. Go through all these plotting and addition of the angles, measurement and addition of the angles. Alternately, you can do it purely with the help of the calculator by simply calculating the modulus and the argument of the real numbers, that of the complex numbers that you get. Check whether 2 plus j2 is on the root locus or not, and if it is, for what value of Ka. But we can apply this immediately to the real axis portion rule, and I'll show you very briefly what the geometrical considerations lead us to. So here is a point on the real axis. So this is the value of S. Now suppose I have a pole on the real axis. Now what are the kind of locations that are possible? We will exclude this point. So there may be a pole which lies here. If the pole lies here, what is the angle subtended by this number S at this pole? The vector simply points from the pole to the point S. It is in the direction of the positive real axis, so the angle is 0. So if I have a point on the real axis, then a pole to its left contributes an angle of 0. Instead of a pole, it could be a 0. What is the angle subtended by S at this 0? It is also 0. So whether there is a pole or a 0 to the left of this point, its angle or argument contribution is 0. Whereas if I have a pole to the right of this point, the vector from the pole to this point is going this way. So what is the angle subtended by this point S, or the angle made by this vector with the positive real axis? It is pi radians. So a pole to the right will contribute pi radians to the argument. A 0 to the right will also equally well contribute pi radians to the argument. Therefore my argument principle now says sum of all angles subtended at poles minus sum of all angles subtended at zeros. If I look at poles and zeros on the real axis, those which are to the left do not matter, those which are to the right only contribute. The poles contribute plus pi because they are in the numerator of that fraction. The zeros, because I am subtracting, contribute minus pi. Now think about therefore what effect this has. On the other hand, if I have a complex pole like this, then what can I say? We have assumed that all the coefficients of the polynomial are real numbers. So if there is a pole like this, there will be a conjugate pole like this. The poles and zeros will occur in conjugate pairs. Now if I look at this point on the real axis, here is the vector from this pole to this point. What is its argument? Its argument, because the angle is this way, it's minus maybe 40 degrees or 50 degrees or plus 310 degrees if I look at it this way. What is the angle made by subtended at this pole? It is this angle going this way. You can see that the sum of the two angles is going to be 360 degrees, but 360 degrees makes no difference to that sum, because angle 30 degrees is equal to angle 390 degrees equal to angle minus 330 degrees. Adding or subtracting multiples of 360 degrees makes no difference to the argument. Therefore, this pair of complex poles will make no contribution to that argument principle method or calculation, because the total contribution of these two will be 360 degrees. If these are zeros, then once again the total contribution will be 360 degrees, but it will be subtracted, and that makes no difference. Whether you add or subtract, it makes no difference if the angle is 360 degrees. Think about this and make sure that you can now derive the rule that I mentioned for real axis portion of the root locus. Why complex plane, that is the poles and zeros which do not lie on the real axis, why they do not matter, why only poles and zeros which lie to the right of a point matter, and why I can take their sum, that is the total number, how that rule comes about. Think about it and then we will proceed further.